Okay, so in the last chapter, we introduced the Schrodinger wave equation and how it's looked on under some idealized circumstances. And now we're going to bring it into the atom, in particular with one electron atoms, because those equations are actually um, solvable analytically. And so we can talk about the wave equation for the hydrogen atom, for example, using the math that we introduced last time. So this is the Schrodinger wave equation for hydrogen. And so you have um, you have it set up so the electron can have x, y, or z components. The potential energy is -1 over 4 pi epsilon naught E squared over R. Again, that's just the Coulomb potential energy from the fact that the proton and electron have the same charge E, but the proton is positive and the electron is negative. So the potential energy is negative, meaning they're attracting each other. And then you still have E, so the total mechanical energy of the electron multiplied by the wave function. So we're not going to derive the solution, but we can still talk about it. So solving the wave equation requires three integer variables. The first is n, the principal quantum number, which we've already talked about quite a bit. That's the n that's come up when talking about the Bohr model and also when talking about the infinite square well. You have those quantized energy states. So that's the n that we're talking about. We also have L, what's called the orbital quantum number, which is related to the angular momentum of the electron. You usually don't see this split in energy levels until or unless the electron is exposed to a magnetic field. But the angular momentum is equal to the square root of L times L plus 1, whatever that value of L is, multiplied by h bar. Again, we have that h bar term popping up. Again, Planck's constant divided by 2 pi. And then we have a third quantum number, m sub L, which is the orbital magnetic quantum number, which is related to the z component of the angular momentum, that L sub z is equal to ml times h bar. So capital L here is the magnitude of the angular momentum. M sub L is the z component of the angular momentum. And remember, the angular momentum vector points in the direction of the axis. So if the electron is spinning in the xy plane, then the the angular momentum vector points in the z direction. But if it's making an angle relative to the xy plane, well, then the z component of the angular momentum is going to be smaller than the total magnitude. And again, the energy states can be separated by exposing the atom to a magnetic field. So finding and defining these energy states required a bit of experimentation, or a bit of further experimentation that we will discuss a little bit further on today. So the quantum numbers are integers. So n can be any positive integer. So starting with 1, 2, 3, and going on as far as is necessary. L can be any integer between 0 and n minus 1. So if you're in the ground state, n equals 1, then L has to be 0. If you're in the second energy state, so n equals 2, L can be 0 or 1. If n equals 3, L can be 0, 1, or 2, and so on. M sub L can be any integer between -L and L. So in the ground state, L is 0, M sub L has to be 0. It can't be anything else. But if L is equal to 1, so if N is equal to at least 2 and you have L is equal to 1, then M sub L can be -1, 0, or +1. So all possible states with the same value of N are said to form a shell. And all possible states with the same values of N and L are said to form a subshell. Quantum mechanics allows for orbits along a sphere rather than simply a circle. And so that's the difference from the Bohr model. The Bohr model assumes circular orbits. In quantum mechanics, you could be the orbit is spherical, and it doesn't have to be a rigid circle, and you're not necessarily the same distance r away either. But we'll talk a little bit more about that as we move on. So for n equals 7, what values can L have? Well, L can be 0, 1, 2, 3, 4, 5, or 6. So going back, it can be any integer between 0 and n minus 1. So you can't go to L equals 7 if n equals 7, but you can go as far as L equals 6. So then we get to what's called spin. And in order to see the difference between the energy levels that correspond to what's called spin, the electron needs to be moving at relativistic speeds. So you have what's called fine structure, or the tiny splitting of energy levels. In order to solve this, in order to find in order to solve the relativistic version of the wave equation, and this was done by Dirac, and that's well too complex for this level of physics. That's graduate level physics. But in order to solve the relativistic version of the wave equation, you need an additional quantum number. So that's M sub s, which is the spin magnetic quantum number. Unlike the other quantum numbers, which are integers, M sub s is a half integer. It's either +1/2 or -1/2. And again, the electron has to be traveling at relativistic speeds for you to see the difference in the energy levels. And so the Pauli exclusion principle says that no two electrons in the same atom can have the same values for all quantum numbers. Now, this exclusion principle made it possible to set up the periodic table based on the ground states of each atom, and to make sense of why certain groups, certain subsets of atoms or elements have very similar properties. So spin angular momentum is, so capital S, it's very similar to capital L. So capital S is equal to the square root of S times S plus 1 H bar. And so that's equal to radical 3 over 2. So S is simply 1/2. And M sub S can be +1/2 or -1/2. And so the Z component of the spin angular momentum is M sub S times H. So it's either +1/2 H bar or -1/2 H bar. So that's H bar, not H. And again, H bar is Planck's constant divided by 2 pi. So the next question for,
when are you going to get me the full wolf book?
give me a minute.
Okay.
Or give me a while, actually. For n equals 6, L equals 3, what are the possible values? Huh?
When's your wolf over?
It'll be over when it's over, Inga.
Dad, but can you just give me a time?
5?
Okay, I know it.
My apologies. For n equals 6, L equals 3, what are the possible values of M sub L and M sub S? So in this, really, it's only the L term that matters for this particular part. So Let's set up the whiteboard. And so we have n equals 6. L is equal to 3. So m sub L is equal to 3, 2, 1, 0, minus 1, minus 2, minus 3. So again, m sub L can be any number between negative L and positive L. So, so you have 7 possible values, and so each has 2 substates. Each of these values of m sub L has 2 substates corresponding to m sub S equals positive 1/2 and m sub S equals negative 1/2. So for L equals 3, you have 14, 7 times 2, possible substates. And so possible combinations of m sub L and m sub S. So now let's take a look at the wave function. So this is the wave function for the ground state of hydrogen, not getting into the relativistic version of this. So psi 100 is equal to 1 over the square root of pi times r naught cubed times e to the negative r over r naught, where r naught is the Bohr radius, which is 0.0529 nanometers. So even with quantum mechanics and going about things a different way than Bohr did, you get this value for the Bohr radius. So you get this value for r naught. And so this term comes from normalizing the wave function. And we'll talk about that a little bit more in a bit. So the ground state is normalized. So, this is the wave function. Remember, the probability states that the probability is equal to the square of the wave function. So you're integrating the probability over the entire volume. So now we're not talking 1 dimension, we're talking 3 dimensions, because the electron moves around a sphere, not around a circle. And so the pi is equal to 1. So the volume, or the differential element of volume, is 4 pi r squared dr. So ultimately, the wave function doesn't depend, doesn't really have a specific x, y, or z dependence, but it does have an r dependence. So it only depends ultimately on the specific distance you are away from the nucleus of the atom. So dV is equal to 4 pi r squared dr. And so you integrate that and you set that integral to 1, and that's where this term comes into play. Now, the radial probability distribution can be written as PR is equal to 4 pi r squared psi squared. And so you're integrating PR over dr from 0 to infinity, and that gives you 1. And for the ground state of hydrogen, PR is equal to 4r squared r naught cubed e to the negative 2 over r 2r over r naught. And the most probable radius comes from setting the derivative of this function equal to 0. And so we're asked to show that the ground state wave function is normalized. So getting back to what we have here, we want to show that this is normalized. So how do we do that? So I'm going to set up the whiteboard. Hopefully I can, this has enough space. So PR dV is equal to psi squared 4 pi r squared dr. And, or rather, this is PRDR. And so, and that's going from 0 to infinity. And so that's equal to, so you have to square the wave function. And so that gives you 1 over pi r naught cubed. And e to the negative 2r over r naught. And that's times 4 pi r squared dr. And so we want to prove that this integral equals 1. So the pi terms cancel out. And so outside the integral, you have equals 4 over r naught cubed. And then within the integral still, you have e to the negative 2r over r naught r squared dr. So anytime you have a fairly complicated function of r or any other variable, especially if one of the terms involves an exponential function, or in particular a negative exponential function, the first thing you want to try is integration by parts. And so the integral of u dv from point A to point B is equal to the product of u times v, again from point A to point B, minus the integral from A to B of v du. Okay, so that's the basic version of integration by parts that we're going to work with here. So we need to set up u and we need to set up v. And we want to set it up so that u gets simpler in case we, or if we need to do this again a second time, that next time u is simpler. So we're going to set u equal to r squared, so that du is equal to 2r dr. So then dv is equal to e to the negative 2r over r naught dr. Okay, and so we want v, we want to integrate over the integrate the exponential. So if we were taking the derivative, you'd be multiplying by negative 2 over r naught. But because we're integrating, that's v is equal to negative r naught over 2 times e to the negative 2 r over r naught. So that's the value of v that we're working with. And so you take the derivative of that, you get back this. So now let's do this. So we have 4 over r naught cubed. And so you want uv, so that's r squared negative times negative r naught over 2 times e to the negative 2r over r naught. And you're evaluating between 0 and infinity, and then subtracting the integral also from 0 to infinity of v, so that's negative r naught squared e to the negative 2r over r naught times 2r dr. So let's simplify both of these. The first one simplifies really easily. The e to the negative infinity is 0, and because there's an r squared term, the function is also 0 at r equals 0. So it's r is equal to 0 at both ends. So this is simply 0. So what that leaves you with is 4 over r, well, you have 4 over r naught cubed multiplied, so the negatives cancel. So it's 4 over r naught cubed multiplied by r naught over 2. So what that leaves you with is, and oh, don't forget this 2 here. So the 2's cancel and the negatives cancel. And so you have 4 over r naught squared. And again, the negatives cancel. And so you have e to the negative 2r over r naught times r dr. So it's a simpler function to work with than what we have, but we're going to need to integrate by parts again. So we'll set u equal to r so that du is equal to dr. And you'll probably see we're only going to need to do this once more. And then dv is exactly what it was before. E to the negative 2r over r naught dr, so that v is equal to negative r naught over 2 times e to the negative 2r over r naught. So we set this up again. So 4 over r naught squared, and you have uv, so r times this. So that's negative r naught over 2 times e to the negative 2r over r naught, evaluated from 0 to infinity. And so you can probably already see that at 0, when r is equal to 0, this function is 0. And when r goes to infinity, the function goes to 0 as well. So this term is again going to be 0. So we have minus, and then you're integrating from 0 to infinity. And so that's v. So that's negative r naught over 2 e to the negative 2r over r naught times dr. So let's set this all up. So again, this term goes to 0. So just like this term did, this term is also going to go to 0. So we have negative signs canceling out again. So now we have 4 over r naught squared multiplied by r naught over 2. So we get 2 over r naught. And now the integral is from 0 to infinity, e to the negative 2r over r naught dr. And this is an integral we no longer have to integrate by parts here. So this becomes 2 over r naught. You take the inverse of that, so that's negative r naught over 2 times e to the negative 2r over r naught, and you're evaluating from 0 to infinity. So because of the negative sign, so you can start with the negative, and so the 2r naught over r naught and the r naught over 2 cancel. So we'll just have the negative sign. And so that's the negative. At infinity, this term still goes to 0. The exponential term still goes to 0. So that's 0. And when r is equal to 0, this term simply goes to 1. E to the 0 is 1, regardless of what you're multiplying that 0 by. So it's 0 minus 1. And so the negatives cancel. You're left with 1. So the probability is 1 this equation was properly normalized. So that's how you do that type of integral. And where was I? Okay. So the probability that an electron is located between r is equal to a and r is equal to b is just p is equal to PR dr. And instead of going from 0 to infinity, you're going from point A to point B, whatever those 2 points are. And so that makes the integral, I mean, you can still do it analytically. You can still do this integral analytically. But, if you're not going from 0 to infinity, you can't assume that certain terms are going to go to 0. So you're going to need to keep track of all those terms because they're not going to go to 0. If A is not 0 or B is not infinity, you're not going to have any 0 terms that you can just cross out and make your life simpler. But you can still do it analytically. Okay, so with the S subshell, when n equals 1, L can, in fact, n can be any number, but in the S subshell, L is equal to 0. So M sub L has to equal 0. And so you just have the two states, M sub S equals positive or negative 1/2. And so you have two possible states in the S subshell. In the P subshell, which corresponds to L equals 1, well, then M sub L is 1, 0, or negative 1. So there are 3 possible values of M sub L, each with 2 possible values of M sub S. That's 6 states. With L equals 2, so M sub L can be 2, 1, 0, negative 1, or negative 2. So 5 possible values of M sub L, 2 possible values of M sub S. That's 10 possible states. And we already did the F subshell for L equals 3. We got 14 possible states. And so you build the periodic table from this. So the ground state of hydrogen, you just have one electron in the 1s subshell. With helium, you have 2 electrons, so you filled that shell. With lithium, you have the 2 electrons corresponding to n equals 1, but then you have to go up to n equals 2 to still be in the ground state. So you have S1, and then beryllium, 2s2. So now you fill the S state for n equals 2, but when n equals 2, you can also have a p subshell. So you get to boron, the 5th atom, you now have the 2p1, and you can keep going from there. And we will in a couple of minutes. But list the quantum numbers for each electron in the ground state of oxygen. So this is a bit simpler than this last example. So oxygen is n equals 8. So you have 1s2. So you fill the 1s subshell, and then you fill the 2s subshell. So that's 4. And then you have 4 electrons in the p subshell, again, corresponding to L equals 1, which you can have when n equals 2. And so that's the ground state of oxygen. And so then you can take it further from there. So you get fluorine and then neon. And so neon has a completed p subshell. And then you do the same thing with n equals 3. And so until you get to argon, which has a completed p subshell. And then you start with n equals 4, but after calcium, You then go to the 3D subshell before then going to the 4p subshell. So it gets a little bit more complicated from that. Notice how the high ionization energy corresponds to the completed p subshells. It's relatively easy to ionize an electron that's alone by itself in the s subshell. But to ionize an electron in a completed p subshell, it's quite a bit harder. And in a completed s subshell, it's quite a bit harder as well. Which brings us to the periodic table. And it's drawn to take advantage of the fact that elements with the same ground state subshells have similar properties. So you start with hydrogen, and then you get what are called the alkali metals and the alkaline metals, which correspond to this is with one extra electron in a new s subshell. So that's what all of these. So lithium, Na is sodium, K is potassium, Rb is rubidium, and so on. And those metals react very well with what are in column 17, which are the halogens, which are gases that are missing one electron in that p subshell. So these elements have an extra electron. These elements are one electron short of a complete subshell. So they react together very, very easily. Column 18 are what's called the noble gases, starting with helium, then neon, then argon, krypton, and going forward from that. They have completed p subshells, which means they don't react as much as the other elements do. They're not as likely to form chemical combinations because they've got their subshells completed, and the need for adding or subtracting, or the benefit for adding or subtracting electrons, is greatly diminished. Basically, atoms like completed shells. And so they tend to make reactions to complete their shells, or to work in terms of completed shells. So elements with similar properties are placed in the same column, and they have similar properties because of their electron structure. So we start with the noble gases, column 18. Full S and P shells in the ground state, it's not easy to get them to react with anything. The alkali metals, column 1, one electron in the new S shell, they react very easily with elements from column 17. And so then you have some more complicated metals, which are the transition elements. They have incomplete D shells, and the actinides and lanthanides have incomplete F shells. So these are the incomplete D shells. Those are called the transition elements. And then the lanthanoids and the actinoids are the incomplete F shells. And so we go all the way, and then you see we're as far as 118 with this periodic table, although a lot of where the writing is sort of gray instead of black, those don't really exist in nature. And they can be created in the laboratory in a very short lifetimes. So how do you figure out the atomic number of a particular element? Well, it turned out that there was a way to do that using X-ray spectra. So for elements with a high Z, a transition to the n=1 state, so going all the way down to the ground state, results in the emission of a photon in the X-ray region of the spectrum. So a very high energy photon. And if a beam of electrons is fired into a metal, the collision will produce X-rays. And there'll be a spectrum of X-rays that will shift as the voltage is varied. So you have this continuous spectrum that depends on the energy of the electron beam, basically. But also two distinct lines called characteristic X-rays that do not shift with voltage, but depend on the substance used. And so this is for potassium. And so again, you adjust the voltage, the continuum part underneath will shift, but K alpha and K beta are characteristic. Okay, so this isn't, the K doesn't correspond to potassium. It's emitted from a molybdenum. Let's say that 20 times fast. A molybdenum target in X-ray tube. And so these two wavelengths are very specific. And it turns out that there is an equation that you can use for a given characteristic X-ray, particularly the shorter wavelength X-ray, K alpha, that's related to Z squared. And so if you know that wavelength, you can figure out Z squared. And because all these other terms are figured out, so you have 1 over n final squared minus 1 over n initial squared. So n final squared is typically 1 in these transitions. N initial squared can be any of a number of different numbers. And so you have the n equals 2 to n equals 1 transition. Instead of being proportional to Z squared, it's proportional to Z minus 1 squared. So this relationship was found out through experimentation. But what it did was it made it possible to determine the atomic numbers of the different elements, especially the heavier elements. And so you can find Z using this equation. And again, it depended on specific emissions of X-rays when exposed to a high energy electron beam, but it made it possible to identify where different substances fit on the periodic table. So now we do an example. Estimate the wavelength of an n equals 2 to n equals 1 transition in iron. So Z is equal to 26. So here again, because it's n equals 2 to n equals 1, you want Z minus 1 squared, not Z squared. So we'll set this up. And so 1 over lambda is equal to 1 over lambda, or at least approximately equal to, and so you have Z minus 1 squared and e to the 4th times m, and you're dividing by 8 times epsilon naught squared h cubed c. So there's a lot of complicated variables that go in, and then 1 over 1 minus 1 over 4. So you plug all these in. So this becomes 3/4. So we can write this as 3 over 32. Z we know is, because it's iron, Z is 26, so Z minus 1 is 25. E we know is 1.60 times 10 to the negative 19. coulombs to the fourth. So you may want to be careful. There might be a limit to the powers of 10 that your calculator can go up to. So you have to be careful not to cross that line. And so M is the mass of the electron. So 9.11 times 10 to the negative 31 kilograms. So you have this term we've already accounted for. That's 8.85 times 10 to the negative 12 coulombs squared per Newton meters squared. And you're squaring that. Then you have Planck's constant, 6.626 times 10 to the negative 34, and you're cubing that. So you need to be extra careful. And then 3.00 times 10 to the 8 meters per second. And so Planck's constant is joule seconds. So that's big and messy. And you have to be super careful with the calculations with this. So let's see if I can get this to work. Okay, so 3 times 25 squared times 1.60 e negative 19 all right, divided by 32 divided by 8.85 times 10 to the negative 12. And you need to do that again. All right, and don't forget to multiply by the mass of the electron, but you have to be careful not to go below 10 to the negative 100 with this. So divide by 6.626. Okay, and then divide by the speed of light. So I get a value for 1 over lambda, and then I invert it, and I get lambda is equal to 1.95 times 10 to the negative 10 nanometers. Remember, visible light is 10 to the negative 7 nanometers. So these are shorter wavelength, which means they're higher frequency, which means they're higher energy photons. So that's the wavelength of the X-ray involved. So let's get back to the lecture slides. So you then have what's called breaking radiation, or in German, Bremsstrahlung. That's when an electron emits a photon as it loses kinetic energy. So HF is equal, and that should be negative delta K, or the absolute value of delta K, because it's losing the kinetic energy. So whatever kinetic energy is lost is given then to the photon. So if an electron slows down due to influence from some sort of nucleus or some sort of collision, what will happen is that it will emit radiation. The shortest wavelength in the spectrum occurs when the electron gives up all of its kinetic energy. So HF naught is equal to E delta V, where E is equal to the potential difference that the electron is accelerated through. So again, going back to this diagram, you have that lambda naught that corresponds to the highest frequency of radiation that the electron will emit which basically equals the kinetic energy of the electron involved. And so you adjust the potential difference, you adjust the energy of the electron. So now we go on to another example. If the shortest wavelength Bremsstrahlung X-rays emitted from an X-ray tube have lambda is equal to 0.027 nanometers, what is the voltage across the tube? So again, that occurs when HF naught is equal to E delta V, and we're given the wavelength. So that's the equivalent of HC over lambda naught is equal to E delta V. So let's set this up. So we have HC over lambda naught is equal to E, and that's delta capital V for the potential difference. And we are asked to find the voltage across the tube. So delta V is equal to HC over lambda naught times E. So H we know. And C we know. So a lambda naught we are given, that's 0.027 times 10 to the negative 9 meters. And E is 1.602 times 10 to the negative 19 coulombs. And this will give us a potential difference. So 6.626 times 10 to the 34 times 3 times 10 to the 8th divided by 0.027 and then divided again by 1.602 E. And you get, after all these small numbers, you wind up getting a fairly large number. So 45,000 or 4.54 times 10 to the 4 volts. So it's a pretty strong potential difference that that electron is put through. And so again, you can see how much the electron, as it slows down, it's emitting radiation, is what that comes down to. Okay, so continuing on. All right. So how do you observe the different energy values corresponding to different values of L? Well, from the Bohr model, and so there's a bit of a difference between how the Bohr model does it and the quantum mechanics does it. Basically, it starts with exposing the atom to a magnetic field. So the magnetic dipole moment, according to Bohr, so the magnetic dipole moment is I times A. And so the current is equal to the charge multiplied by how quickly it spins around the atom. And the area involved is pi r squared. So it's sort of like a circular loop of wire in the Bohr model. And so The frequency is equal to the speed at which it moves divided by 2 pi r. So the distance divided by the circumference, or rather the speed divided by the circumference. And then again, you're multiplying by pi r squared, and you get 1/2 times E times V times R. And you can write that in terms of the angular momentum, 1/2 E over m times L. For quantum mechanics, we know that the dipole moment is E times H over 2m. So you just take the value of the total angular momentum, or the magnitude of the angular momentum, and put that in. So EH bar over 2m multiplied by the square root of L times L plus 1. So this relationship works even outside the Bohr model. And so you can set it up so that you have a value for the magnetic dipole moment. And if you remember from physics 2, that if you expose a dipole moment to a magnetic field, the rotation will orient itself so that the dipole moment vector tries to line up with the magnetic field, and it orients itself so that the electron will alter its spin so that its dipole moment lines up with the magnetic field. So basically, you're minimizing potential energy. And so the potential energy of a dipole moment in a magnetic field is equal to negative mu dot B. And so if you set up the magnetic field so that it's in the z direction, you get negative mu z bz. And so you have a potential energy for the electron. And so you can write that as E h bar over 2m from this times m sub L times bz. So remember, you have the suborbital quantum number. And so m sub L. And so you can figure out the z component of the angular momentum. And from that, you get this relationship. And so we define what's called the Bohr magneton, E h bar over 2m times m sub L times b sub z. And so you can then separate the energy states by exposing it to a magnetic field. You're altering the potential energy. And so the quantity mu sub b, again, E h bar over 2m. It's called the Bohr magneton. It's equal to 9.7 times 10 to the negative 24 joules per Tesla. And so what the Zeeman effect says is that an atom placed in a magnetic field would have its energy split into levels that differ by delta U is equal to mu sub b times b. And so this is the Stern-Gerlach experiment. And so it's this was the first observation of the Zeeman effect. So theory led experiment in this case. And so theory said that that split in energy levels had to be there. It took Stern and Gerlach to make the experiment to prove it. And so if the spin angular momentum is affected rather than the orbital angular momentum, then delta U is equal to 2 times mu b times b. Again, the magnetic field. So verify that the Bohr magneton is the value the given value that it has. So that's E times h bar over 2m. So we can write that as E. Times h bar, so that's 6.626 times 10 to the negative 34 joules per second, or joules seconds. And then, so we're dividing by 2 pi and then dividing by 2 here. So we have 4 pi in the denominator and 9.11 times 10 to the negative 31 kilograms. And so again, you set up the math, and you're getting good practice working with powers of 10. And so I'm getting 9.26 times 10 to the negative 24. And again, that's joules per Tesla. All right, so moving to another example. If the quantum state of an electron is specified by these four quantum numbers, N, L, ML, and MS, estimate the energy difference between these states, so 100 minus 1/2 and 100 positive 1/2 of an electron in the 1s state of helium in an external magnitude of 2.5 Tesla. So going back to show that, so going back 2 slides, for the spin angular momentum, it's 2 times the Bohr magneton times B. So we can just put that in. So delta U is equal to 2 times the Bohr magneton times B. So that's 2 times, what was that number again? A 9.27 times 10 to the negative 24 joules per Tesla. And then B is 2.5 Tesla. And so you plug those numbers in, you get 4.6 times 10 to the negative 23 joules, and you can write that if you want as 2.9 times 10 to the negative 4 electron volts. So it's a fairly small energy difference, but again, it's significant enough that it's, you get that energy state, you get different energy states, and it makes it possible to have multiple electrons with fairly similar energy states. So we've talked about orbital angular momentum, and we've talked about spin angular momentum. Well, it turns out that if you combine the two into a total angular momentum, which you would do by vector addition, that the total angular momentum is quantized fairly simply as well. So capital J, the vector capital J, is equal to the vector capital L plus the vector capital S. And you can write the magnitude of J as equal to the square root of small j times small j plus 1. And that square root is multiplied by h bar. So it's not all that different from figuring out the orbital angular momentum or the spin angular momentum separately. So small j is equal to L plus 1/2 or L minus 1/2, with the stipulation that j is always greater than 0. So if L, which basically means that if L is equal to 0, then j is equal to positive 1/2. Otherwise, there are two possible values of j. So there are a couple of other properties that we're going to talk about that, basically, that are quantum phenomena. The first is called fluorescence. So in fluorescence, an electron is excited by a UV photon and then emits visible photons as it returns to its initial state. So certain substances will glow if you expose them to ultraviolet radiation. So you put them in UV light, so you don't actually see the UV light, but it glows in the visible. And why is that? Well, it takes in a high energy photon, but then it emits smaller energy photons to get back to its initial state. So instead of emitting one high energy photon back, it emits a couple of smaller energy photons instead, but you can see those, or at least see some of those. And that's what fluorescence is. So you expose it to UV light and it emits something in the visible. So you can make things glow under ultraviolet light. Another property is called phosphorescence, where the electrons reach a stable excited state and then gradually emit photons as they return to their initial state. So you're given a certain amount of a certain amount of high energy radiation is absorbed by the substance, and eventually the uh, the substance will settle back down to its unexcited state. But in the meantime, because the excited state was stable, its lifetime is fairly long. So it doesn't re-emit the radiation all at once. It emits it fairly gradually and over time. So if you have something that glows in the dark, well, what's happened is it's been exposed to a certain amount of radiation, and and so the material has been, you know, sent up to an excited state, but it takes time to uh, to cool back down, for lack of a better way of putting it. So it's re-emitting the radiation, but only very slowly, because the energy that came in excited the electrons to a high end state that's actually fairly stable, which means it doesn't, the electrons don't get emitted back out right away. And so, or the photons don't get emitted out right away. So again, the radiation is emitted back out slowly over time. So this is called phosphorescence. And so that's glow in the dark. You think fluorescence, that glows under UV light. Phosphorescence can glow in the dark. So this watch, for example, has some, I don't know if you can really see it. It has some phosphorescent material in this. So if you turned all the lights off, you wanted to find out, let's say you wake up in the middle of the night and you want to find out what time it is. Well, if you grab the watch, which has been absorbing light this whole time, it's re-emitting that light fairly slowly. So you might be able to look and see what time is on the watch without having to turn the lights on. Because again, this particular watch has some phosphorescent material. And so that's basically how it works. And the last thing we're going to talk about today are lasers. And lasers obey a principle called, or work under the principle of stimulated emission. So a photon of a specific wavelength can, if the rules of quantum mechanics allow, cause an excited electron to emit a photon of the same frequency that is exactly in phase with the incident photon. So the best analogy I can make to this is that if you're, let's say you're playing a guitar string and you're playing up on the fretboard so that the note you're playing corresponds to the note of one of the open strings of a higher pitch, of a higher frequency. And so when you play that, the open string of the same frequency will start to vibrate on its own. So now you have two strings making the same sound. And this will happen if the strings are tuned fairly closely to each other. And so that's kind of what's going on here. It's a similar property of waves that uh, you expose an excited electron, or you just put it in the presence of the right wave, it will and it has enough energy to emit a wave at that, or a light wave at that same frequency. It will do that, and that light, or that emitted light, will be exactly in phase with the incident photon. So quantum mechanics makes this possible, but it's basically a wave-like phenomenon. And so it's both quantum, and it's related very directly to its wave-like properties. So think sympathetic, strings, and it's very much like that. And so in a laser, you get a cavity where you have a whole bunch of electrons that are excited, and you expose them to light of this frequency. It only takes one photon to be emitted at that frequency to trigger the emission of the other electrons, or the emission of that same photon completely in phase, from the other excited electrons. So these photons are coherent, which means they oscillate in phase with each other. So what do you need to create a laser cavity? So you need what's called an inverted population, meaning more atoms are in the excited state than in the ground state. So you need something to excite the atoms. And the state not only has to be an excited state, but it has to be a metastable state. So this goes back to what we were talking about with phosphorescence, that you excite them, but they don't re-emit the radiation right back. So it has to be a metastable state. So the atoms will remain in that excited state unless they're stimulated by incident photons. And so there are two types of lasers. You have a pulsed laser where the energy input and output is periodic. So, it emits pulses. And you have a continuous laser where the energy input and output is continuous. Pulse lasers, the beams from pulse lasers tend to be very powerful, but only over very small periods of time. So the two different lasers serve different functions. So one last problem, and then we're done. A laser used to weld detached retinas puts out 23 millisecond long pulses of 640 nanometer light, which average 0.63 watts output during a pulse. How much energy, and so that's joules per second. How much energy can be deposited per pulse, and how many photons does each pulse contain? So so you need to go, you're asked for joules per pulse. So you're given that it's 0.63 watts. And so a watt is a joule per second. So you can write that as joules per second. And you want the number of joules per pulse. And so how much energy can be deposited per pulse? So you want the number of seconds per pulse. And so you can times this by one pulse. Um, so you want seconds per pulse. So 23 milliseconds. per 1 pulse. And so this gives the amount of energy that's put out over that 1 pulse. So that's 0.63 times 23 times 10 to the 3. And that gives you 0.014 joules per pulse. Or 0.014 joules per pulse, excuse me. So how much energy can be deposited per pulse? And then how many photons does each pulse contain? So you want to convert the 0.014 joules into a total number of photons. So NHF is equal to, so that's the total amount of energy in the pulse. And so is equal to 0.0114 joules. So the total amount of energy per pulse. So we can write that also as, since we're not given the frequency, we're given the wavelength. So we can write that as N times C over lambda. And so now we just want to solve for N, where N here is not a quantum number, it's just the number of photons. So N is equal to lambda, so we'll call this E, the energy per pulse. So that lambda times E, and I'm forgetting an H, which would, so it looks like that. So N is equal to lambda times E divided by H times C. So that's lambda, which we're given, it's 640 nanometers. So (0.014 joules divided by Planck's constant. So you can see this is going to wind up being a pretty large number of electrons. And then 3.00 times 10 to the 8 meters per second. So the presence of Planck's constant in the denominator is going to wind up making this a pretty large number. So you get 4.7 times 10 to the 16. So that's how many electrons that you have. 4, 7 with 15 more zeros added on. So 9 is a billion, 12 is a trillion. So 47 quadrillion electrons in the pulse of the laser, or photons, excuse me, in the pulse of the laser. Okay, then, so that's all we're covering for today. That's it for chapter 39. So on Friday, we will do an experiment on the Rydberg constant, and we will go over problems from this chapter. So I will see you then.